Good morning, students. So, in up to this extent, we are discussing that how the bearings are going to be selected for the rolling contact bearings based upon the different types of working conditions, as well as we seen that. So, the type of load the bearings are subjecting is only a constant type of load, that is a steady load. That is whatever the magnitude of the load we are considered, that is not going to change with respect to the change of time. But coming to the actual practical applications, so 90% of the bearings or the machine components that are subjected to the fluctuating type of loads, that is variable loads. So as I stated that in the previous case, so the type magnitude of load, for example, it is a 10 kilonewtons. So it is acting on the component with a period of some 10 seconds. So which is a steady time. So if case for each second of the time the load magnitude may varies, and the type of load is fluctuating load, or it may also call it as variable loads. So these machine components can also subject to the variable type of loads. In that case, so how the bearings are going to select, that we will discuss in this class. So that is a selection of bearings, that is a rolling contact bearings subjected to the variable loads. Clear? So let us come to this case, as I stated that the load magnitude is going to change with respect to the time. So for that case, I am going to take the magnitudes of the loads with the regular intervals of the times. So that is some T1, T2, T3 time periods I can consider. So for that cases, I take the load magnitudes of P1, P2 and P3, or the loads acting on the bearing for the successive speeds of time intervals of T1, T2, T3 and the speeds of N1, N2, N3 number of revolutions, that is N1, N2, N3. So we know that as we also know that, so if the bearing is operating under working loading conditions, so the total life of the bearing can be calculated by using the relation. So that is L equal to C by P whole power K million revolutions. That is as we discussed in the earlier case also. So this is the total life of bearing in million revolutions. It is given by C by P whole power K. We know that what is C, what is P. So C means that is the dynamic load carrying capacity, and P is the equivalent bearing load, and K is a constant, that is equal to 3 for ball bearings and 10 by 3 for roller bearings. That we know that. So this is the total life of the bearing subjected to the load. So in million revolutions it is given. So if case, for example, the fraction of life that consumed for one number of revolution, that is a one complete revolution, and the life can be given by 1 by L1. That is for one revolution, the life consumed is given by 1 by L1, and that can be written as P by C whole power K into 1 by 10 power 6. Why? Because it is a number of revolutions. It is a fraction of life in, not in million revolutions. So here we are writing in million revolutions, but here we are writing this as a number of revolutions. This is the fraction of life for one revolution, so that I can written as 1 by L1. So it is written, can be written as P1 by C whole power K into 1 by 10 power 6 number of revolution, that is a 1 for one revolution. So similarly for fraction of life consumed, so with the load P, so as I stated that, so the magnitude of load is not same during throughout the time period. So here the total work cycle, that is one complete work cycle, can be divided into some number of sub cycles, that is even half period and another half period, or 1/4, 1/4, 1/4, that is a 1 quarter cycle, to the 4 1/4 quarter cycles, you may get one complete work cycle. In the similar case here, I can divide it into the complete work cycle into 3 number of time durations, so that during the N1 number of revolutions I can take the load as a P1, then the life consumed for the N1 number of revolutions can be given by, so that is similar to this case, so P1 by C whole power K into, so it can be multiplied by N1. So as I stated, this is the fraction of life consumed for one number of revolution. Similarly, if the fraction of life can be consumed for N1 number of revolutions is given by, so this multiplied by N1. So clear? So we can similarly we can also write for the remaining fraction of lives for remaining loads or remaining time durations, that is for N2 and N3. So let us see. So it is a fraction of life consumed for P2 and P3 loads. So for N2 and N3 number of revolutions, then the life number of revolutions, that the fraction of life corresponding to the number of revolutions given by P2 by C whole power k into N2 by 10 power 6 and P3 by C whole power k into N3 by 10 power 6. So clear? So this is the fraction of life consumed during that particular period of time. So in the previous case we can see that is a P1 by C whole power k into N1 by 10 power 6, that is a fraction of life that consumed during the first slot of, that is the first time period, and this is the life fraction of life consumed for the second period of time period, and this is the fraction of life consumed for third period of time interval. So if, for example, if you want to calculate the total life cycle, that is the total life consumed during the one complete life cycle or complete work cycle, can be given by all the lives that consumed during the regular, that is during the 3 intervals of time. So that you can sum of these, all these can be given, that is N1 P1 power, that is N1 P1 power k by C1 into 10 power 6, that is the fraction of, this is the fraction of life consumed for first interval of time, that is N1 speed. So similarly, this is the fraction of life, that is P2 by C whole power k into N2 by 10 power 6. This is the fraction of life for the second interval of time, and N3 P3 power k by 10 power 6 C power k, which is the given by, that is a fraction of life consumed for third interval of time. So that if you want to give the total life of the bearing during one complete work cycles, gives the sum of individual lives that can be consumed during that particular time interval. So that the summation of all the time intervals, that is a fraction of life consumed during all the time intervals, can be given by the total life consumed during one complete work cycle. Clear? So this is, I can consider this is an equation 1. So like that, if you have x number of life cycles, that is time cycles, time duration cycles, so that I can also write, so up to x extent you can get the total life of the bearing for one complete life cycle. So we also know that the equivalent bearing load can also be written as, so if you want to calculate the total life cycle consumed during the life cycle, the total life can be consumed is given by n into Pe power k by C into 10 power 6. So here, so where n can be written as the total number of revolutions, that is N1 plus, that is number of revolutions in the first time cycle, and N2 is number of revolutions in the second cycle, and N3 is number of revolutions in the third cycle. Likewise, up to how many number of cycles you may have, up to that extent you can sum, you can get the total number of revolutions that the bearing can operate. So using that you can calculate these. So this equation, so which means it is given by equivalent load for the complete work cycle, you can written as n into Pe power k by C into 10 power 6. So by equating equation 1 and 2, so from that you can write this equation in this form. So C power k and 10 power 6 may get cancelled, and n into Pe power k will be equal to N1 P1 power k plus N2 P2 power k plus n, up to that n how many number of time periods you may have, up to that extent you can write. So n we can write, you know that n can be written as N1 plus N2 plus N3. So from that Pe power k can be written as in this form. So that you can observe, so this is N1 P1 power k, N2 P2 power k, up to x number of time cycles you may get the equivalent load. So simply you can written as, it is given as sum of the n, that is the number of revolutions, into loads. So that is P is the loads acting at that particular time interval, n into P power k, that is sum of all the time intervals, gives the numerator, and denominator can be written as the total number of revolutions that bearing can operate during the one complete life cycle. Clear? So in this equation, if you observe clearly, so as we discussed in the earlier sessions, that is selection of the bearing under the static load conditions, the P1 can be calculated, that is P, that is the equivalent load can be calculated using the XVFR plus YFA into V, that is S, service load. So XVFR plus YFA into S. So in a similar case, in this equation also, the P1, P2 up to Px, thus those equivalent loads can be calculated by using the same standard equivalent dynamic load equation, that is XVFR plus YFA. But in this case, the similar case, for calculating those equation P1, P2, P3 up to Px, if you have, so all these equations we need to calculate. After that, we need to calculate the equivalent bearing load in a variable load. So by using this equation. So in that case, you can calculate only one single equivalent load, but in this case, for each interval of time, we need to calculate each dynamic bearing load, that is like P1, P2 up to Px. After calculating all these equivalent loads, we need to calculate equivalent bearing load or equivalent load rating for variable loads using this expression. So in some of the cases, instead of the speeds of the or the revolutions of the bearing, that is capital N, we can also use the time intervals, that is a T1 instead of N1. Here we can use T1 or T2 up to Tx, and similarly the denominator we can also write the total time period T1 plus T2 plus T3. So likewise you can also substitute in terms of time duration, that is instead of number of revolutions you can use the number of seconds. In some of the cases, based upon the given data, you can change the equation. Clear? So here, so up to this, the selection of the bearing procedure is the same that for the steady load, but here we need to calculate the equivalent load include using the variable load condition. So we need to calculate P1, P2, P3, how many number of time cycles they can give. So you can calculate those number of equivalent loads, and finally you can calculate the equivalent bearing load using this equation. Clear? So let us go with the simple example for this. The bearing subjected to the variable loads. So let us see. Here, so it is an example problem for bearing subjected to the variable load. So here you can observe it is a ball bearing operating consists of three parts. So as I stated that it is not completely within the time duration, the load is not same. So which way the total work cycle can be divided into three parts. It is clearly stated. So the complete one work cycle can be stated into three different parts. So three different magnitudes of loads we may get. So the first case, so that is a radial load of 3000 newtons is given. So at 1440 rpm for one quarter cycle. So that is a one complete cycle can be divided into three parts. So first part is one quarter cycle, that is 1/4 part of duration. The load acting is 3000. And the second one, that again the radial load, it is 5000 newtons. And the speed is given, which is a 1/2 cycle, that is a 1/4, and the remaining cycle is again 1/4. So again it is a radial load of 2500 newtons at 1440 rpm for the remaining cycle. So as we see that, so all the three cases, the type of load is only a radial load. There is no any axial load is given in the data, so that we don't need to use the expression of XYFR plus YFK. So here P1 is directly equal to the radial load, that is FR, that is FR1. So similarly P2 can be equal to FR2, and here also P3 can be equal to FR3. No need to use the equivalent dynamic load equation XVFR plus YFA into S. So you can directly take, it is only subject to the radial load, that is a pure radial load. So that may be equal to the equivalent load. So no need to use this expression. Clear? So and the expected life of the bearing is given, that is a life in hours, 10,000 hours. So calculate the dynamic load carrying capacity of the bearing. So based upon that you need to select the bearing. So we know that the bearing can be selected based upon the dynamic load carrying capacity of the bearing, that is C. So let us see. So clear. So here, so P1 is given 3000 newton, that is equal to FR1. So pure radial load. But the speed N1 can be given. So they mention the specific speed at that particular load application, but it is not a number of revolutions that the load can be acting upon it. We need to calculate N1. So N1 is given by, so N1 equal to 1/4 into 1440. So that is a 1/4 cycle of the time duration that the specific speed is there. So we need to calculate N1 is given by 1/4 into 1440 rpm, so that we may get 360 rpm. Similarly for N2, so it is 1/2 of 720 rpm, that is 1/2 cycle. So with the speed of 720, and the number of revolutions is given by 1/2 into 720. Similarly the remaining cycle is 1/4, so 1/4 into 1440 rpm. Clear? So this is what the given data, that is again LH is given. So we need to calculate the life in million revolutions and the equivalent dynamic load in a variable condition PE and calculate C. First coming to the equivalent dynamic load in a variable load. So as I stated, this is the equation we need to remember for this. So here so P1 is equal to FR1, P2 is equal to FR3, FR2, and P3 is equal to FR3. And N, so N1, N2, N3 we already calculated that. So the sum of the speeds is given by N. So and K is the constant for ball bearings, it is taken as 3. So if you substitute all the values in this equation, we may get the value of 3823 newtons. And the life in hours is given, LH is given 10,000 hours. So we need to calculate life in million revolutions in order to calculate the dynamic load carrying capacity of the bearing C. So C equal to P into L power 1 by K. So here L is calculated, L equal to 60 N, LH by 10 power 6, that you know that. So LH is given and the speed N can be taken as the total number of revolutions that can be operated, N1 plus N2 plus N3. So you need to take N as that is a 1080 number of revolutions. So we can calculate the life in million revolutions, 648. So then we can calculate the dynamic load carrying capacity, that is C. So now coming to the dynamic load rating, so that is from load life relationship we need to calculate the dynamic load rating, that is C equal to P into L power 1 by K. So P, that is using the variable load what you have calculated. So that is given by 3823 newtons and the life is 648 million revolutions. You can calculate the dynamic load 33 kilonewtons using this dynamic load carrying capacity, as similar to that in the previous case under the static load conditions, how we are going to select the bearing. In the similar fashion, using the dynamic load rating of the bearing, we need to select the suitable type of bearing, starting with the light series bearing to the heavy series bearing, that is using the trial and error method. Clear? So how the bearings are going to be selected, the selection procedure is same. Instead of having the single equivalent dynamic load, here we have the number of dynamic loads. So using those, we need to calculate equivalent dynamic load in variable loading, that is sum of the P into N, that is N into P power K by N, sum of the N whole power 1 by K. Using that, you can calculate after getting the value of C. You need to calculate the suitable type of bearing. It depends upon the dynamic load rating. Clear? So this is how the bearings are going to be selected for dynamic loads, that is using the dynamic load under variable load condition. And next, coming to the another topic, that is reliability of bearing. So what is reliability? So as I stated, that is a reliability. For example, for clear understanding, I can take an example of some batch of products. So you can take in products of some 100 number of products in that. So suppose out of the 100 number of products, so 100 number of products are working effectively in that group of products. So clear? So which means the product reliability is 100%, which means very much reliable the product is. So if suppose so out of the 100 number of products, the product is working only a 50%, then the reliability we said it is said as only 50%. So clear? So which means the amount of working up to the extent how much it is going to work under the actual loading condition, it is going to set the reliability. So if you say that if it is operating up to that extent, suppose if you take a product, they can give a 2 years of warranty. If it is work up to the 2 years without any operational that is what call it damages or anything disturbances, then the product is very much reliable. For example, if you take a product, it is going to fail within the 2 or 3 days of your purchase, then you are going to does not rely any on this service or their product. Here in the similar fashion, so if the product is operating very much effectively up to the given extent, then we call it as the product is very much reliable, then you go into trust that product. In the similar fashion, the bearing should also operate with great reliability. So here the reliability can be defined as the number of bearings that can operate up to L million revolutions to the total number of bearings. For example, you can have the 100 number of bearings in a batch. So the 90% of the bearings can operate a L number of million revolutions without fail. Then the reliability is said to be 90%. Otherwise, if the 100 number of bearings, it is very good to operate. If the 100 number of bearings can operate up to L number of revolutions, L million number of revolutions, then the reliability is 100%. If it is only 50% of bearings, that is only 50 number of bearings are operating, then the reliability is only half. So which is not good at all. So the reliability is defined as a number of bearings which are successfully completed L million revolutions to the total number of bearings under test. Clear? So here according to the Weibull, so we have the relation between the life of the bearing to the reliability. So that is given by log E 1 by R equal to L by into whole power B. So from that we can write L by A equal to log E into 1 by R whole power 1 by B. So where L is the life, you know that here L is the life corresponding to the reliability. So if it is a reliability at 90%, the life is at 90%. The reliability is 100%, the life is at 100%. The reliability is 80, life is at 80. So here the life of the L is represented as life of the bearing corresponding to that percent of reliability. Clear? And A and B are the constant. Next, coming to these cases, so as I stated that L is the life of the bearing corresponding to the reliability, desired reliability, and A and B are constant, that is given by 6.84 and 1.17. So if you want to calculate the life at 90%, so as I stated that during the life of the bearing, so in the bearing industries, the life can be calculated based upon only the life at 90%. So whatever the life you are mentioning up to this extent, that is a life at 90%. So clear? So here if you want to calculate the life at 90%, so that corresponding to the reliability 90. So you can simply written the first equation as L90 by A equal to log E1 by R90. So here life at 90% reliability whole power 1 by K. This is written as second equation. So now dividing the equations 1 and 2, so that A and A get cancelled. So we get L by L90 equal to log E1 by R. So again here life can be corresponding to the R. So that is whatever the life you can take here, that corresponding to this much of reliability. So and divided by L90, so that is life at 90% reliability. Here it can observe R90 whole power 1 by K. So V is constant 1.17. So here this expression is going to use whenever in the problem you may get the life other than the 90%. Then if you want to get in life at 90%, as I stated that, so wherever we are going to calculate the dynamic load capacity C, we can use the life at 90%. In our problem, in our designs, if they supposed to provide a life other than 90%, we are going to apply this equation. Clear? Let us see an example for that. So here, right, is an example problem for the reliability concept. So here the bearings are given. So the speed of the bearing is given, that is shaft speed 720 rpm, and the bearings having the 99% reliability and the corresponding life is given 24,000 hours. That is a life at 99% reliability, which is L99. So they mentioned the life other than 90%. So that is not L90, it is L99 in terms of hours. So the bearing is subjected to an equivalent load of 1 kilonewtons, and you need to calculate the dynamic capacity C. So here they clearly mentioned at 90% reliability. So we need to convert life at 99% to the life at 90. Then we can calculate the dynamic capacity C using the relation P into L power 1 by K. So let us given data, load is given 1 kilonewton, and life at 99, that is in hours, 24,000 hours, and the speed as 720 rpm. Here life at 99 is given, we need to convert the life at 99. So LH99 is given. So we need to calculate the life at 99 in million revolutions. So we can calculate using the relation 60 LH by 10 power 6. So we may get in million revolutions. As I stated, if you want to calculate life at 90%, at 90% reliability L90, so we can use this relation L99 by L90 into log E1 by R by log E1 by R whole power 1 by B. So using that L99 is known, and R99, which means 0.99, and L90 is not known. We need to calculate R90 means 0.99 and B is a constant. So we can substitute it, we may get 0.106. Using that we can calculate the life at 90%, L90. So using this L90 and load is given 1 kilonewton, we can calculate the dynamic load rating. Here it is a dynamic load rating C, that is given by, so P into L power 1 by K. We need to take L90, so not L99. So for that case we use that equation. So C is given by, so P into L power 1 by K. So and P is given and the L90 is calculated. Using that we may get the load. So again, based upon the dynamic load rating capacity of the bearing, we need to calculate, that is select the suitable type of bearing from the manufacturers. Based upon these type of dynamic load rating, we need to calculate the suitable type of bearing from the manufacturer's catalog. Clear? So the selection of the bearing is very much similar to the steady load conditions, but only the thing we need to follow here is we need to calculate the equivalent load corresponding to the variable load conditions, that we have the P1, P2, P3, P1, P2, P3. So in that case, in that fashion, we need to calculate the equivalent load to the variable load conditions, as well as if the life at other than 90 they can go with the variable equation, we calculate the life at 90. So for calculating C, so finally we need to calculate C to select the bearing. So here we need to remember the students, so the total steps in selection of the bearing is only 3 that we must remember. We need to calculate the equivalent load, so whether it is a static condition or variable load condition. If it is a static, the equation is only one, XVFR plus YFK into S. If it is a variable load, we need to calculate P1, P2, P3 and calculate PE. So, and the second state, that is the second step is only the calculating life, that is the mentioning life in million revolutions. If they can give directly at life at 90, it was okay. It is life other than the L99, or that is other than L90, you need to apply the Weibull equation so that you can calculate life at 90% reliability. So, and finally, the third step you need to calculate is dynamic load capacity, that is C, using the load life relation. So, using that dynamic load capacity, we need to select the suitable type of bearing for our given application. Clear? So that we can finish the unit number 1. In the next classes, we are going to see how the designs of IC engine components is going to be in the next class. Thank you.